Okay, now we will try to see some example problems, and we are going to go two categories. One is toy examples, toy problems, and the other one is real world problems. And we'll try to formulate each of the problems. Okay, so a toy problem is intended to illustrate or exercise various problem-solving methods. This is a kind of, a skeleton and the kind of benchmark that is used to compare different methods. It is widely used while you performing research in order to compare different solutions, different approaches for a problem. It can be given a concise, exact description and hence is usable by different researchers to compare the performance of algorithms. So this is consider a simple, concise, precise, and a kind of a problem with exact description, easy to idealize and easy to perform action with. So one such example is a vacuum cleaner, and there are other examples we will be looking in a while. Okay, the other category, other group of problems are known as real world problems. A real world problem is the one whose solution people actually care about. So this is a real life or real world example, and uh, people try to design or determine an actual suitable solution for such problems. So these kind of problems has strong impact on the human life. That's why we consider and we take these examples serious and try to uh, devise a proper solution. Such problems tend not to have a single agreed upon description, but we can give the general flavor of their formulation. Since it is a real world problem and there are different approaches from different minds about each problem, because everyone thinks from different perspective while dealing with the problem. So one such example is a root finding problem. This is a real life problem, and we face this problem in real life, in daily life frequently. Okay, so let's consider the first example, which is vacuum cleaner. We have seen this example in the previous lectures as well. Okay, so first we need to decide number of possible states. So number of possible states, there are 8 possible states. Initial state can be any state. In any state the vacuum may be have in any state. Actions, the vacuum can move left, it can move to right, and it can perform action, that is to suck the dirt. Okay, transition model. So transition model is a complete space, but it can go anywhere from left, right, and it can suck. Okay, the what is going to be the goal state? The goal state is when all the squares are clean, there is no dirt. So the goal test is to see if there is any dirt. If yes, then this is not a goal state. If there is no dirt, everything is clean, this is the goal state. And this is to see the no dirt is what is the goal state, goal test. Okay, path cost. So one move, either move to left or move to right, is like each step is costly. I mean, it costs one single step. So this is the possible states space. Now see, this is the, for example, let's say it's the initial state. So both the squares are dirty and the vacuum cleaner is in the left square. From here, there are three possible actions. So if the vacuum cleaner try to move to the left, it will arrive in the same state because it can't move to the left. So there is a loop. I mean, it will come again to the same state. If it tries to go to the right, so it will arrive in this state. Now you can see the vacuum cleaner has moved to the right. Now if it wants to perform an action, not go to the left, not go to the right, rather suck the dirt, so in case of this action it will arrive in a state where uh, the dirt has gone because it has performed the dirt cleaning operation, it is sucked. So now you can see that there is no dirt in the left cell. Okay. Now for example, okay, it moves to the right. So it came over here, this is the new state. Now the vacuum cleaner is in the right square. From here, if it wants to perform the right action, it will arrive in the same state again because there is no uh, valid right move. If it wants to again move to the left, so it will arrive in this state. And if it wants to suck, then it will arrive in this state. You can see there is no dirt in the right. Okay, now this is done. Come here. Okay, from this state, if it wants to go to the left, so it will arrive in the same because nothing is here for, to move to the right. If it wants to clean the dirt, so it will again arrive in the same state because there is no dirt. If it wants to move to the left, so it will arrive in this state. In this case, the vacuum cleaner moved to the left square. From here, if it wants to go to the right, it will come to this state. If it want to move to the left, there is no left move because the vacuum cleaner can't move to the left because there is nothing on the left side. If it sucks, it will arrive in this state. Okay, so this is done. Now here, from here, if it wants to go to the left, nothing happens, it will arrive in the same state. If it want to sucks, because everything is clean here, again it will arrive in the same state. If it want to move to the right, it can, so it will arrive in this state. From here, if it want to move to the left, it will arrive in the same state previously. If it want to move to the right, it can't, it will arrive in the same state again. If it want to suck, it will arrive in this state where everything is clean. Now from here, you can see if it want to go to the right, it can't. If it want to go to the suck, arrive in the same state. If it want to go to the left, it can go to the left. From here, left, no, suck, everything is clean, no dirt, no, same state, right. So now here you can see everything is clean, so this is our goal state. So from any state here we can start. So any state can be our initial state. Possible actions are suck, right and left. Okay, the transition model is that it can go to any state given any action, and the goal state is this one. Everything is clean, and each action, go to the right or go to the left or suck, costs 1 unit. So this is how you formulate a problem. Now, another problem is 8 puzzle problem. In this you have this grid. In this grid you have these tiles inside the grid. You need to make the tiles in order in any sequence 1 2 3 4 5 6. It can be like this: 1 2 3 4 5 6 7 8. Okay, and one empty. So the task is to make the tiles in order. Okay, states location of each tile and the blank. So I mean any combination of these tiles with an empty location can be a state. Initial state can be anyone, and the possible states, if you try to calculate all these states, the possible states are 9 factorial minus 2, are excluding 2. That is because some states are invalid states. From that state you can't go to the solution. Okay, actions, blank, move. Oh, okay, so actions, or if there is a blank, so these two can move to the move down. If there is blank, it can go towards left. If there is blank, it can go towards right, and in case of this 3, it can go up as well. So there are 4 possible actions: left, right, up, and down. The transition model is given a state and action returns the resulting state. So if this is a state, okay, we give this state to the transition model, and we want to move this 2 to the down. So the new state will be 7 4 5 2 6 8 3 1. This is transition model. The goal state is this configuration, or in case of each step, each move costs 1. So you need to get this with the lowest cost. This is another example, and we have formulated this example. Okay, the other example is 8 queens problem, and this problem is that you need to place the queens on a chessboard such that no queen attack the other. So the attack means that no queen should be in the row of other queen, should not be in the row of in the column of other queen, and should not be in the diagonal of the other queen. So you have a empty chessboard, and you need to put these 8 queens such that it's such arrangement that no queen can attack the other. So what could be the states? Any arrangement of 0 to 8 queens on the board is a state. Any arrangement. Whether it is empty, this is a state. Whether there is 1 queen, this is a state. If there is 8 queens, this is a state. So any arrangement of 0 to 8 queens on the board is a state. Initial state, no queen on the board, so initial state can be like the chessboard is empty. Action, add a queen to any empty square. So action is, let's say if you have this chessboard empty, and the action could be to put a queen and place it on any location on the chessboard. So this is action. You can't remove. You just need to place. You need to think in that place. Transition model, return the board with a key added to a specified square. So for example, if you initially it is empty, you put a queen over here. So now the transition model is to give you a chessboard with a queen here from an empty chessboard. Okay, the goal test is 8 queens on the board, none attacked each other. So that would be your goal test. And the cost is putting 1 queen is that costs 1. Now all these examples were toy examples, and now we are going to see some real world problems. So one real world problem is routing finding problem. Root finding problem. So we have seen this, that for example the agent want to go from Magdan city to Peshawar. So the task is to find the best possible route. This is route finding problem. The other one is touring problem. Now in that problem. This is a kind of route finding problem, but in Turing problem, the agent need to visit each city at least once, at least once. So that problem is uh, what is called Turing problem. The other problem is traveling sales problem. Now in this case, it is a kind of Turing problem, but with a specific limitation, you can say constraint, that the agent has to visit, the agent can visit uh, any city exactly once. It can't visit a particular city more than once. So this kind of problem is traveling sales problem. The other one is Turing problem, and the first one was route finding problem. Now the fourth one is robot navigation. This is the generalization of route finding problem, but in this case, the agent is a robot. And for robot, the normal actual route finding problem has been made simple for the robot navigation with limited actions. And the last problem is internet searching. If you let's say if you want to search something on the internet and you agent is software robot, so this problem can be a real world problem, and we can formulate all these problems. We will see how to formulate in advanced chapters. Okay, now how to represent the problem space. We have seen how to formulate the problem, now how to represent the problem space in order to find the solution, and you can say search for a solution. So there are two methods to do this. One is to form a tree and then search the tree, and the other one is to form a graph and then try to search that graph. So search tree generated by initial state and possible action. So we always build this tree like this. For example, this initial state, and from initial state we can go to this city, we can go to this city, and we can go to this city. For example, we go to this city. Now from this city we can go to add again, other city, and other city, and this other city. So this is how you build a tree. Now the basic idea is to offline simulated exploration of state space by generating successor of already explored states, expanding states. So this is what we do. We get a state and then we see that from that particular city, what are the possibilities of going to other cities. Now the choice of which state to expand is determined by search strategy. There must be a search strategy, and that search strategy will let us know that whether from Array to go to Cebu, or from Array to go to Timisoara, and whether you want to go to Zered. So this decision was basically calculated by the search strategy. Now, there are some terminologies we need to have a clear concept of while dealing with the search space in tree search and graph search. One is frontier. We sometimes refer as open list. Set of all leaf nodes available for expansion at any given time. Now, in this example, you can see when you are in array, you can go to Cebu, you can go to Timisoara, you can go to Zered. So these are the frontier, and this list is what is called frontier or open list. So open list, set of all leaf nodes available for expansion at any given time. Okay, there can be repeated set. If you visit a state, if you like arrive in a state more than once, then we can say that this state is basically a repeated state. A loopy path, arid to Cebu and Cebu to arid. Now this is you can see here. For example, if you go to Cebu from arid, and from Cebu you uh, arrive again in arid or go again to arid. This can be termed as loopy path. Okay, redundant path. More than one way to get from one state to another state. Okay, if there are more than one routes from one place or from one state to another state, then those can be considered as redundant paths or redundant path. Sometimes redundant paths are unavoidable. Okay, so there are cases where you have to follow the redundant path. You can't avoid. Uh, we have seen this in example of 8 puzzles here. So there is a one way of this blank. You have to go frequently from this path. For example, you want to put this 3 over here. So this will go from here, and then after some time it will go to this place. So in this case, the redundant path is unavoidable. Okay, and then the last one is search strategy. The search strategy basically tell us that if there are more than one state available to move from this state, then what path should the agent follow, or which state is suitable for agent to go to. So this decision and this process of making the decision is what is called search strategy. Okay, this is the general tree search algorithm. So this algorithm is followed for searching a tree. And you know what does search mean? Search mean to find the solution. So we formulate a problem and give this problem to tree search algorithm, and in return we get a solution, or if there is no solution then we get a null or failure. Okay, first we need to initialize the frontier. That is, for example, this is our initial state. So the frontier is empty, and now if this is our initial state, then the open list of frontier will contain these 3 cities, because from this city we can go only to these cities. These are directly connected to arid. So first we need to populate the frontier. Okay, if the frontier is empty, then return failure. Okay, let's say if we can't go anywhere from this state, then your frontier is empty. Okay, and there is no solution. If this is not true, then you need to select any of the node from the frontier. For example, if you want to go to Cebu, we'll remove this from frontier and will perform action go to the Cebu. If the node contains a goal state, now if we arrive this Cebu, we will perform goal test. If this is our goal state, if the node contains a goal state, then return the corresponding solution. Okay, if this is goal state, then you need to return the solution that you need to perform go action from arid towards Cebu to get the solution. If this is not a solution, then you need to expand this one. Now you need to expand these the other cities from Cebu. So now the frontier, uh, in the frontier list, we will have these cities, not these. Okay, because now we have seen the frontier is all the possible states that can be achieved from the current state. So these are the possible states that can be achieved from the Cebu. So now frontier list will contain these four cities. And this algorithm goes and goes. Tree search can visit a state multiple times, and as such it will explore the subtree found after this state several times, which can be expensive. So in tree, uh, the repeated states are possible in uh, tree search algorithm. Okay.